Hi and welcome to the third part of a tutorial on asynchronous programming using the C# programming language. This video is also the third part of the sixth tutorial in an advanced C# course. In the first and second parts of this video series, we looked at how to apply asynchronous code so as to alleviate the negative effects of blocking operations on an application's UX, user experience. Certain long-running operations performed by our applications can be the source of poor performance of our applications. For example, long-running operations performed from WPF, UWP, or Xamarin applications can cause the UI, user interface, to be periodically unresponsive. This can be frustrating for the user of our applications. The user will have a suboptimal user experience. C# provides us as developers with appropriate tools to handle these long-running operations asynchronously with relative ease. So let's discuss the difference between I/O-bound operations and CPU-bound operations, and this will set us up for later when we create a code example to help us understand best practices when applying asynchronous code to handle I/O-bound or CPU-bound operations. So in this video series, we have already discussed that the two kinds of CPU blocking operations are CPU-bound operations and I/O-bound operations. CPU-bound operations are operations that perform computations that need to be handled by the CPU, for example, mathematical operations, encryption-decryption operations, graphics-related operations, financial calculations, etc. Basically, computational operations. I/O-bound operations are operations that are delegated to the I/O subsystem to perform tasks such as writing to a hard disk drive, engaging the I/O subsystem to perform requests across the network, file handling operations, etc. We discussed that I/O-bound operations are more commonly encountered than CPU-bound operations. I/O-bound operations are also generally a lot slower than CPU-bound operations. So this video is about best practices when applying asynchronous code in our applications. Please view the first and second parts of this video series on asynchronous programming for a foundational understanding of I/O-bound operations and CPU-bound operations in the context of asynchronous programming in C#. The recommended coding methodology provided by Microsoft in the C# language to create asynchronous behavior in our applications is known as the Task-Based Asynchronous Pattern, TAP. Over the last two videos in this series, we have discussed why we should implement asynchronous code. The simple answer is to improve the performance of our applications. In this video, let's clarify the best practices when applying writing code to run the relevant code asynchronously. Let's start with I/O-bound operations. As we have discussed, I/O-bound operations refer to operations like, for example, file handling operations, making requests across a network, writing data to a database, reading data from a database, etc. Operations that engage the I/O subsystem. We can handle I/O-bound operations asynchronously, both on the client side, for example, in WPF, UWP, WinForms, or Xamarin applications. We can also handle I/O-bound operations asynchronously on the server side, in, for example, Web API or ASP.NET MVC applications. I/O-bound operations can be handled using async await. In simple terms, an asynchronous method that returns a task object can be preceded with the await operator, which means we can run the operation asynchronously using async await. So, for example, for a .NET client application, a button is clicked. Within the button click event handler method, an asynchronous method is invoked. So the asynchronous method is invoked on the UI thread. This means that immediately after the asynchronous method is invoked, the UI thread is free to be utilized to process other operations. The user interface, UI, does not freeze while the asynchronous method is running. The user is able to, for example, click other buttons and invoke other operations that can be invoked on the UI thread. When an asynchronous method is called to perform the relevant I/O-bound operation, the task is immediately delegated to the I/O subsystem. And instead of blocking the CPU, as would be the case if we were running the IO-bound operation synchronously, the async modifier and await operator instruct the .NET runtime to ensure that the CPU is not blocked during the running of the IO-bound operation. This means that other operations can utilize the CPU even while the IO-bound operation is running. Very briefly, what is happening is that when the .NET runtime encounters the await operator, as discussed, the thread on which the operation is invoked, on the client this would be the UI thread for example, is immediately released. So at this time, code in the relevant method is suspended, i.e. the lines of code that follow the line of code that contains the await operator in the relevant method will not be executed until the asynchronous IO-bound operation completes. While the asynchronous IO-bound operation is running, however, the UI thread can be used to process other operations, for example, invoked from clicking another button on the UI. But a promise is returned to the line of code containing the await operator is made. So when the relevant asynchronous operation completes, the .NET runtime returns to the line of code containing the await operator, returns a value if required, and continues to execute the lines of code from that point in the relevant method. So the key point of this explanation is that unlike for CPU-bound operations, IO-bound operations generally don't require additional background threads. In this example, the .NET runtime is delegating the IO-bound operation to the IO subsystem and not to a new thread required from the thread pool. So I think before we continue, let's ensure that we have a clear understanding of what is meant by the following terms: thread and thread pool. Let's start with the term thread. A thread in computer science is short for a thread of execution. Threads are a way for a program to divide itself into two or more simultaneously or pseudo-simultaneously running tasks. Thread pool. A thread pool is a group of pre-instantiated idle threads which stand ready to be given work. So, a thread pool is created so that threads are readily available to a program, which means when a program requires a thread, the program can acquire the thread from the thread pool rather than incur the overhead of instantiating a new thread. So, let's go back to the example demonstrated in the second part of this video series, where the Task.Run method was used to run CPU-bound operations. We demonstrated how each method that was run through the implementation of the Task.Run method was run on its own dedicated background thread. So each time the Task.Run method is invoked, a new thread is taken from the thread pool and used to run the relevant CPU-bound operation. So this resulted in the methods that encapsulate the CPU-bound operations running concurrently, i.e. asynchronously, rather than running one after the other, i.e. synchronously. If you haven't yet viewed the second part of this video series, please view this video for a foundational understanding of running multiple CPU-bound operations concurrently on multiple background threads. So the key takeaway here is that when an IO-bound operation is run using the async modifier and the await operator, a background thread is not required to handle the operation. The operation is delegated by the .NET runtime to the IO subsystem. When a CPU-bound operation is run using the Task.Run method, a background thread is used to run the operation in the background concurrently with the main thread of execution. So now, with a foundational understanding of the differences of how IO-bound and CPU-bound operations are handled asynchronously, let's look at best practices regarding implementing each of these types of operations asynchronously. So with running IO-bound operations asynchronously, there's less to be concerned about, simply because of the way the IO-bound operations are handled under the hood. IO-bound operations can be delegated to the IO subsystem, and the need to use additional background threads is not necessary. With running CPU-bound operations asynchronously, under the hood, the .NET runtime employs additional background threads to run the CPU-bound operations. This, for example, means that multiple tasks can run on the additional background threads concurrently. There may be times where using multiple threads is undesirable and may not result in the desired performance benefit. There are times when running multiple threads to perform tasks in parallel may result in an overall poorer performance. An example of this is running CPU-bound operations from within server-side code, for example, code implemented for ASP.NET MVC applications or code implemented for Web API components. We'll discuss why CPU-bound operations should be run synchronously under these scenarios a bit later in this video. So let's create a code example to help us understand best practices when confronted with issues relating to asynchronous programming in C#. The theme of this client application will be the same as the theme we used in the previous video in this series, i.e., a financial trading platform. So in the last video, we created a console application to get a general idea of running CPU-bound operations. In this video, let's create a new blank UWP project. UWP stands for Universal Windows Platform. Let's name this project Financial Trading Platform UWP. Let's set up a basic UI, user interface. Let's drag a button onto the designer surface Let's enlarge this button a bit. And name it BTN Fast Local Operation. Let's label this button Fast Local Operation. Let's drag another button onto the designer surface, just below the button we have just added. Let's name this button BTN CPU Bound Operations. Let's label this button CPU Bound Operations. And lastly, let's drag a list view control onto the designer surface and position this control to the right of our buttons, like this. Let's name this list view control LVW output. So before we add code directly to this file, let's add another project to this solution. We want our code to be reusable across both server-side and client-side projects. So let's create a standard library project to our solution and let's name this project Stock Market Component. Let's add a reference to the Stock Market Component standard library project from our UWP client project. Let's delete the class file that has been generated in our standard library project and let's add a class named stock market data to our project. Let's add a method named getDataAsync. This method represents retrieving relevant stock market data from a server, so it is an I/O-bound operation. The method will return a string to the calling client code. So let's include the async modifier in the method definition, as well as a generic task type that accepts a string as the data type argument. Notice that we have included the async suffix in our method name. This lets the developer know that this is code that should be called asynchronously. So when the calling client code writes code to call this method, the developer should include the await operator preceding the method call, as well as include the async modifier in the method definition of the method where the relevant async call resides. So in the interests of time, we'll simply include placeholder code for this method. So let's use the Task.delay method to represent the time that the work could take to carry out our relevant I/O-bound task. So let's say this process takes 5 seconds. So let's pass 5,000 milliseconds to the Task.delay method. Let's then simply return a string value representing the stock market data that has been retrieved from the remote server. So let's simply return the literal text stock market data from this method. We must also include the await operator preceding our call to the Task.delay method. Let's add a new class, and let's name this class Stock Market Data Analysis. So let's add a constructor that contains a parameter named data, which will represent the downloaded stock market data. For the purposes of this example, we don't need to include any code within the constructor. So very much like the code example in the previous video of this video series, let's include methods that calculate the technical indicators that the user of our application can use to aid the user's decision to buy or sell a quantity of a particular stock. The technical indicators that we'll refer to in this example will be the fast-moving average, the slow-moving average, stochastics, and Bollinger Bands. If you are not familiar with these terms, don't worry. The only thing that you need to know to follow along with this example is that calculating the data for these financial trading-related technical indicators are CPU-intensive. They are CPU-bound operations. This is why I've chosen these technical indicators for this example, i.e. to serve as intensive, long-running, CPU-bound operations. So let's include a method to calculate the fast-moving average. So for these methods that represent CPU-bound operations, we can simply put the current thread to sleep for a specified amount of time, representing the time that the relevant operation may take to complete. So for this method, let's put the thread to sleep for 6 seconds. Then, for the purposes of this demonstration, let's simply return the method name and the thread ID to the calling code. Let's duplicate this method 3 times. These additional 3 methods represent the calculation of other technical indicators. So we can maintain the general structure of the methods that we have just created as they are, and simply change the method names and the time durations that represent the time the method takes to complete. Please note that the time durations that are being specified here are completely arbitrary and have been chosen only for demonstration purposes. So this method represents calculating the slow-moving average. Let's name this method calculate slow-moving average. Let's put the relevant thread to sleep for 7 seconds. This method represents calculating the stochastics. Let's name this method calculate stochastics. Let's put the relevant thread to sleep for 10 seconds. This method represents calculating the Bollinger Bands. Let's name this method calculate Bollinger Bands. Let's put the relevant thread to sleep for 5 seconds. Great, so let's say that we now have a reusable standard library component for calculating stock market technical indicator information completed. So just to confirm that we have already referenced this reusable component from our UWP client application. Great, so let's add some code to add the output of our methods to our list view control that we named LVW output. So let's create a private method named addListItem. So you're of course welcome to follow me as I create the code for this method, or you can of course copy the code from GitHub. A link to the relevant GitHub repository is available below in the description. Great, so let's include code within our button-click event handlers. To create a button-click event handler definition, we can simply go to our designer surface and double-click on the relevant button, like this. So we are first going to create code for the fast local operation. So let's create the button-click event handling method definition for the method that will execute our CPU-bound operations. These CPU-bound operations are encapsulated within the methods in our stock market data analysis class that reside in our standard library project. Let's ensure that we have a directive to the stock market component namespace. So let's instantiate an object from our stock market data analysis class, which resides in our stock market component standard library project. For now, let's simply pass in the literal text data to the constructor of the stock market data analysis class to represent the raw stock market data downloaded from a remote server. So let's write code first to run all of these CPU-bound operations in parallel to one another in much the same way as we demonstrated in the code example in the previous part of this video series. So firstly, let's create a list of generic task objects that accept the string data type as their data type arguments. So we know that the task.run method returns a task object or generic task object. The methods we wish to call all return strings, so each item in the relevant list must be strongly typed with a generic task object that accepts the string data type as an argument. Right, so let's add the tasks we wish to run to our list, like this. Then we can call the task.WhenAll method, and in a bit I'll explain why the task.WhenAll method is not the best method to call in this context. So in the code following the task.WhenAll method, we know that the relevant methods that have run asynchronously have completed, so we can add the returned values from our methods to our LVW output list view control. Let's write the code to do this. Right, let's run the code. So now when I press the button marked CPU bound operations, notice that our UI is unresponsive when we try to perform any other operations. So I'm attempting to click the button marked fast local operation. The button cannot be clicked because the screen is frozen, and therefore the output from this action is not presented to the screen in our list view component. The UI is unresponsive when I click the button labeled fast local operation, because the UI thread is blocked. We have written our code to run a batch of methods asynchronously, but we have also written code to block the UI thread while our CPU-bound operations are running. The WhenAll method blocks the UI thread until all the relevant tasks have completed. So even though the CPU-bound operations, like for example, calculate stochastics, calculate fast-moving average, etc., are running in parallel to one another on background threads, the UI thread is being blocked while these CPU-bound operations are running. This is not ideal. So we can solve this issue because we can in fact use the await operator when running a batch of CPU-bound operations. We can achieve this by using the WhenAll method instead of using the UI blocking waitAll method for running a batch of CPU-bound operations on background threads. So let's replace the waitAll method with the WhenAll method. For more information on the WhenAll method, please navigate to this URL. So please note that the waitAll method does not return a task object or generic task object. So this means we cannot call this method using async await. The waitAll method blocks the UI thread until the tasks within the relevant batch have completed. The tasks will be run concurrently on separate background threads, but the UI thread will be blocked while the tasks are running. The WhenAll method, however, does return a task object or generic task object. This means we can call the WhenAll method using async await, which means that we can call the WhenAll method to run our tasks concurrently without blocking the UI thread. The UI will still be responsive even while we are running a batch of CPU-bound operations when we are using the WhenAll method. So let's proceed our call to the WhenAll method with the await operator, like this. We of course need to also include the async modifier in the relevant button click event handler method's signature, like this. Let's run the code. Let's click the button marked CPU-bound operations. And now when we run the code, the UI thread is not blocked and we are able to perform the fast local operation while the CPU-bound operations are running in the background. We can perform other operations concurrently while the relevant CPU-bound operations are running. So the Task.run method returns a task object or generic task object. This means we can use the await operator when we call a CPU-bound operation in this way. So to prove this, rather than calling a batch of CPU-bound operations, as we are doing here, let's run just one of the CPU-bound operations using the Task.run method. So let's run the calculate stochastics method using the Task.run method. So we can call this method on a background thread asynchronously like this. Let's run the code. Let's click the CPU-bound operations button, and you can see that while the calculate stochastics method is running, we are able to click the fast local operation button. The fast local operation button can run concurrently with the operation performed by the calculate stochastics method. And as we have already proven, We can also run a batch of CPU-bound operations on background threads without blocking the UI thread using the WhenAll method. So let's change the code back to the way it was so that we can call a batch of CPU-bound operations using Task.Run, async await, and WhenAll. Then we could reuse this functionality because we have written our CPU-bound operations in a reusable library component. This brings us to an important best practice when implementing asynchronous code for CPU-bound operations. The developer should never include the task.run method within reusable components. Always let the developer decide whether to run an operation synchronously or asynchronously. So the consumer of the component should always have the choice to run an operation contained within, for example, a library component synchronously or asynchronously. In our example, we have chosen to run our operations encapsulated within the stock market data analysis component project asynchronously, but we could have chosen to run them synchronously. We have proven in our demonstration that running the CPU-bound operations asynchronously gives us a huge performance advantage. We did, however, have the choice to run these operations synchronously or asynchronously because the operations are not implemented to run asynchronously within any of the methods of the component itself, i.e., we have not implemented the task.run method within the stock market data analysis component project. So in the stock market data class, we have written an IO-bound operation that is responsible for downloading the raw stock market data from a remote server. This is different to a CPU-bound operation because it engages the IO subsystem and not the thread pool to acquire a background thread. So let's write code to run this IO-bound operation in order to download the relevant raw stock market data before calculations are performed from the raw stock market data. So we could invoke the IO-bound method lazily like this. So let's create a member variable named _data. Then within the relevant button-click event handler, we can check to see if the _data variable is null. If it is null, we can then run the IO-bound operation. If the _data variable is not null, then it means we have the data and can pass it into the stock market data analysis classes constructor when instantiating the relevant object. It is best to include the task.run method close to the relevant event handler method, as we have done here. We have control over whether we want to run these operations using the task.run method on background threads or run them synchronously. So calling the task.run method directly from the relevant event handler method, like for example a button-click event handler, is a best practice. Another best practice is that if the relevant method's code doesn't need to run on the original thread once the CPU-bound operations have completed, then we can in fact gain a bit of a performance boost by not returning to the main thread. The rule of thumb here is don't run code on the main UI thread unless you have to. So we can achieve this performance boost by using the configure await method. So the WhenAll method returns a task object, which implements the configure await method. This means we can call the configure await method like this. Notice we are passing in false as the parameter to this method. We are saying that after the calculations are performed by the CPU-bound operations, don't return to the main thread. So for example, a context where this would be appropriate would be once the calculations are completed, we want to save the calculated data to a file. So in this scenario, we don't want to display the data on, for example, a stock market chart. We only want to save the data locally. In this context, there's no reason to return to the main thread. However, in a context where we need to display the information on a chart, we of course would need to return to the main thread. The last best practice I would like to include in this video is that we should avoid including the task.run method within methods implemented in server-side components. If, for example, we implemented our trading platform calculation functionality as a software-as-a-service application for the purpose of providing calculated technical indicator information to web-based client trading platforms, we should not implement these CPU-bound operations using the task.run method. On the surface, it may seem like this would give us a performance advantage, but in reality, this puts an unnecessary strain on server resources and ultimately can adversely affect performance. The reason for this is that with a server-side component, say for example implemented as an ASP.NET Web API component, you may have thousands of HTTP requests coming in to the relevant Web API component. Each HTTP request requires a thread from the server's thread pool. If the code within the relevant server-side method is coded to run 4 operations asynchronously through the use of the Task.Run method, then your Web API component needs to acquire an additional 4 threads to carry out the instructions implemented in the relevant method. This could cause an unacceptably high use of server resources, which could adversely affect the overall performance of the relevant server and ultimately negatively impact the user's experience with the relevant application. So the moral of this story is avoid running additional background threads on the server side. Rather run CPU-bound operations synchronously on the server side. You can still ensure that the client-side UI is responsive by calling the server-side code using async await. Remember, an HTTP request from the client's perspective is an IO-bound operation. Note that running IO-bound operations on the server is different to running CPU-bound operations on the server. An example would be downloading the raw stock market data from the server. Perhaps the server-side code simply retrieves the raw stock market data from a database before returning the relevant data to the client. This IO-bound operation can be written on the server using async await. The IO-bound code does not require additional threads and therefore additional server-side resources. When a client request is made to run the method responsible for running the relevant IO-bound operation on the server, the thread used for processing the request can be released to handle other requests while the relevant IO-bound operation is being performed. CPU-bound operations that are invoked using Task.Run will require additional threads, which means additional server resources will be required. In summary, when it comes to best practices in terms of asynchronous programming in C#, know the nature of your asynchronous code. Ask the question, is the operation CPU-bound or IO-bound, and then apply the relevant asynchronous code appropriately. Avoid writing CPU-bound operations within reusable library components using the Task.Run method. Let the consumer of the library component choose whether to run the CPU-bound operations synchronously or asynchronously. Methods that run IO-bound operations asynchronously, included within reusable library components, should include the async suffix as part of the relevant method's name. This will let the consumer of your library know that the relevant method should be run asynchronously using async await. On the client side, run CPU-bound operations close to the relevant UI event handler method. For example, use the Task.Run method directly within the relevant button-click event handler method. If, for example, a button-click event handler method needs to perform a CPU-bound operation asynchronously on a background thread and subsequently code within that method does not require a return to the UI thread, explicitly let the .NET runtime know that it is unnecessary to return to the UI thread once the CPU-bound operation has completed by appropriately calling the configure await method. This can result in a performance boost. Avoid running CPU-bound operations on the server side using the Task.Run method. These operations require additional threads, which can result in a strain on server-side resources, and the issue will be compounded if the server is handling hundreds or thousands of HTTP requests. Running IO-bound operations, for example, retrieving information from a Web API component, reading data from a database or writing data to a database on the server side using async await, is good practice because the main thread of execution is free to handle other client requests while the relevant IO-bound operation is running. So in this video, we covered how to implement best practices in our code when running code asynchronously in C#. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future videos released from this channel. If you feel you've gained value from viewing this video, please smash the like button. It will be greatly appreciated. Please feel free to share any of the videos created by this channel with anyone you feel may benefit from their content. I love reading your comments, so please feel free to share your thoughts with me in the comments section. All code created in these videos can be downloaded from GitHub. Please see below in the description links to the appropriate GitHub repositories. Thank you, and take care.